I will try to follow up now and talk about some ideas that we have on where things go from here. For the uninitiated, let me explain again this metric, floating point operation per second. This multiplication here is what we mean by one floating point operation. This addition is a second floating point operation. So what you have here are two floating point operations. A petaflop means we have 10 to the 15 of these per second. A gigaflop, let me start because that's where our words still work, is a billion or eine Milliarde or 10 to the 9 of these floating point operations. So that's what the first applications did some 20 years or 24 years ago, was 10 to the 9 or eine Milliarde solche Gleitkomma-Operationen pro Sekunde. Now there is two ways to measure, or no, there's multiple ways to measure this. One way is to just measure the theoretical maximum that the machine can have. And sometimes in newspapers you read that number, and a lot of centers will talk about that number, which I think is about the most meaningless number you can look at. There's nothing about what you can do in theory. The next measure is this, what you heard sometimes, the top 500 list, or the Lindback number, solving an idealized linear set of equations, and that would be a more realistic measure, but still not representative of applications. What I'm showing on this slide are what really applications, so simulations in fluid mechanics, in material science, or in seismology, do when they run on these machines. And as I said, the first gigaflop was sustained on an 8-processor machine in 1988. A very similar machine was standing a few years later at ETH Zurich, and I did my PhD work on that machine. 10 years later, the first teraflop, or now 1,000 billion floating point operations per second, was sustained by a project actually running by colleagues at Oak Ridge National Laboratory. I already moved there, but I was not part of those projects. And another 10 years later, the first petaflop was sustained on a machine, and this was this machine Jaguar that Domenico mentioned in his talk. And so given this development, the prediction is that, because this is a factor 1,000 every 10 years, and I guess everybody can do the math, that in 2018, 10 years later, we will have another factor 1,000, or now 10 to the 18, which is a billion times a billion floating point operations per second. There are people who are scared of this number. When people make projections about what will this machine look like, they cannot imagine what this machine, and trust me, the computer experts, the architects cannot imagine what this machine will look like. Now, I dare to make the prediction the machine will exist and it will be built, even if the computer architects don't know how to build it at this point in time. And this is going to be the argument I'm going to make. And I understand I'm aggressive, but I guess that's what you have to be in the business of science when you try to look into the future. And the reason they are scared is because of these developments. We have a factor 1,000 improvement, but we have a factor 100 going every 10 years in the number of processors involved. And if people imagine what this machine looks like, they will say, well, it's going to be even more than a factor 100 that we need in terms of processing elements. And the reason is because of this other development that is also scaring the people who have to fund these instruments. And that is, computers went from 100 kilowatts, the largest computers, some 20 years or 10 years ago, to megawatts today. And this is one of the main drivers why we build a new building, because in order to run a petascale system, we have to run a system that runs multiple megawatts. We have to cool it, and we have to do it in a cost-saving way. And that is why we built this new building. And so, if people imagine and make optimistic predictions, they talk about tens of megawatts. So this is one thing that gets a lot of us thinking, okay? But I totally agree that we have to really focus on efficiency and energy efficiency. There's no question about that. But I would like to put my finger on another trend. And that is, unlike the previous machines, this machine and several other machines at the same time. So IBM built the first machine that sustained a petaflop on this Limpac that was built from cell processors, which are commodity processors built for PlayStations. This machine was built from AMD Opteron processors, the same processors you would use in a PC at the same time. So this is one of the changes that happened, and I believe this is the market that will fuel the development that we will see an exaflop. Okay? I know there are many colleagues who totally disagree with this statement, okay? But I think there is a simple argument, and that's an economic argument behind it. I have this from Andy Keene a few years ago. He presented this. It takes to develop a processor $500 billion. So either you have the cash to pay $500 billion to a company, and they will develop the processor you want. And the second biggest machine today, fastest machine, the K computer in Japan, was actually built that way. They did pay Fujitsu $500 million. The entire project costs $1 billion. So to bring the K computer to life cost $1 billion, just to give you the scale. Now, this is not how we build computers anymore in the US, and this is not how we build the computers here. So if you want the company to invest $500 million, they will need revenue, and that's what the $2 billion mean here, to basically justify this investment. Okay, that's simple economic arguments. If you were to fund this just with HPC, with scientific computing, individual processors would cost $13,000, which is at least a factor 10 more than we want to pay, because there's many thousands of these in there, in the machines that we run here. So unless there is a market that funds this part here, there will not be this investment. Or unless there is somebody that funds this part, we will not continue to grow scientific computing. The market that has a lot of affinity with what we do in scientific computing is movies and games. And you heard before from Domenico, actually, thank you for making this argument. Today, movies and games are built on animations, okay? In order to make games more realistic, which is what our kids want. I see it with my son. They want more realistic games. The companies who build these machines understand that they have to go from animations to simulations. And then the market that drives this is becoming very similar to scientific computing. So we have the market that will fund the development. I'm very convinced of this. Or a large part, the expensive part of the development. Now we need problems. Do we have problems in science that can use this scale? And in this point, we've heard a beautiful talk on the Earth science modeling simulations in seismology. You can derive an argument there. I want to go back to another field that is very practical, and this is a long-standing collaboration between CSCS and Meteo Suisse, and the systems that run the weather forecasting for Switzerland. As we speak now, they are working behind us. So just some, practically how this works. There is input data that comes from the European Centre for Mid-Range Weather Forecasting in the UK that is then fed into a simulation at 7-kilometer resolution that is running here 3 times a day, a 3-day forecast. Now with this, you can not predict weather in Engadine or here in Ticino because the resolution is just not good enough. So then this data is fed into a 2-kilometer resolution simulation that runs 8 times per day and for a 24-hour forecast. And this is then what Meteo Swiss is taking in order to do the products that we see on TV, but also the products that keep our airplanes from flying safely and not dropping out of the sky because we made wrong predictions about the weather. And even in the case of if we had any severe events happening in Switzerland, then the management of the situation after that will be based on these products that Meteo Swiss is creating. It turns out the climate scientists, at least at ETH, use very similar models. And what you see here is how a thunderstorm is forming. And this is what we would call an ab initio simulation, because all it takes is known properties of, equation of state from water, vapor, ice, and atmospheric physics. And at a relatively high resolution, I've written it here, 0.5 kilometer resolution, they can really describe the formation of clouds. Now, a recent breakthrough that happened in the group of Christoph Scher is that they showed that these weather cloud resolving simulations of climate or weather are actually converged at 1 or 2 kilometer resolution. So you don't have to go, arbitrary further in terms of the resolution. And this is an important news because when you look at what the climate scientists today do at ETH, very similar to what Meteo Swiss is doing, and this is a collaboration between ETH, Meteo Swiss, and CSCS. We are part of ETH, so it's ETH and Meteo Swiss in developing these codes. So it's a very similar application. The difference is just that they make currently predictions for 10 years instead of a few days. And that's the difference between weather and climate. Okay? Now, the point that I'm making is you can, and so this is real. And with now new codes that come out of this HP2C platform, we can say, how do we take this to the next IPCC runs? Okay? Well, we need to do, instead of 10 years, we have to go a factor 10 here. It turns out this factor 10 we can deliver with new codes and the machines we have. Okay? Now, given that this is qualitatively going to be a much higher climate simulation than what we had in the past, you can say, well, why don't, instead of doing it over just the Alpine region, why don't we do it for the entire globe? And there's colleagues in Boulder, Colorado, there's people around the world that are thinking in the same way. Now, all I'm saying is the good news, if these simulations happen at this 1 or 2 kilometers resolution, going from these 1,000 or million kilometers square here to the globe, which is 500 million kilometers square, is just a factor 500. So all we need to do is scale up the machines. And this is the type of things that this seismology, material science, there's problems in all areas that are going to be customers for exascale computers. So we have a market that drives it. We have the problems, the users, and I believe if you put these two things together, there will be machines that use exaflops in 2018. The question is, how do we organize the work? How do we, Domenico made the point. Somebody needs to make sure we can program the machines and so on. So let me quickly reflect on the process on how you go from a model. I put climate slides here just because I had them, but you could put a geophysics problem here or a material science or a chemistry problem, biology problem. It's a physical model, a mathematical description, a set of equations, in this case, Euler equations. You then need to discretize these models because the computers are digital machines, so you need to discretize them and you need to create algorithms. Then you need to translate the algorithm into a code, and because it's humans who write the code needs to be readable by humans. And then this code needs to be translated onto some machine. and this is an automated process called compilation into a machine-readable language. Okay. Now, this is the textbook example that we would teach our students how things ought to work in scientific computing. I deliberately put the Cray YMP, this is the machine I did my PhD on, because that's how things actually worked 20 years ago. Okay. The world has changed since then, and there is a problem when we go, usually this step we develop, when we go from here to here, we have problems. And then we talk about adapting codes, vectorizing codes, parallelizing codes. In Brace, we use the language petascaling and exascaling. Okay? And this is what you would naively think is the help CSCS should give you. Okay? The point is, I do not believe that this is how things work. Okay? And this is why we need to change or think differently about these things. The reality is we don't have these nice supercomputers of the past anymore. What we have is actually a better situation. Namely, as I said earlier, we have a commodity market that is driving, has to solve similar problems. So it will create beautiful processors, and it does. For example, the IBM iDataplex system that was inaugurated a few months ago, 1 month ago, in Munich, which is the biggest system in Europe, the most powerful system, is built out of this Intel Sandy Bridge processor. We have a choice of processors, and that means we have a design opportunity, which we can take advantage of. And once we take this, and we still have everything above, and we think about the relationship between things, we see that things are much more interactive than they are unidirectional, as we thought they are before. So there's interactions going up here. There is still this compilation process, but the architectural choices will impact algorithmic developments, and they will impact developments of the software. And so how do you organize this type of complex environment to create a complex machine? I think the important point is just that we realize what are the driving forces behind this. Well, one thing is the domain scientists, people like Professor Giardini, they will drive this. Okay, you have seen the excitement, and you see it in every scientist. They will just continue to drive this. In the same way they build experiments, they build models, and they build simulations, and they build the mathematics around that. The other drivers, natural drivers, are the vendors. And it may be politically incorrect to say that they are drivers, but that's just because of the way economy works. Okay? So we have companies here, IBM, Cray, HP, SGI. There's a number of companies that have economic reasons why they will continue to drive this. I know governments have sometimes the illusion that they can drive it, but I don't think in the end they can help, but the drivers are just where there are bigger markets. So the question is how we properly embed these developments that we tend to forget about into these boundary conditions here. And there is an argument you can make that vendors, through services that they offer, take care of this problem. And the scientists just focus on science. That's something you hear sometimes. If I was a vendor, I would definitely argue this way as well. Now, in Switzerland, we don't really have to subsidize computer industry like some of our other neighboring countries do or think they have to do. So we can take a very pragmatic approach. And this is what we do with this HP2C platform. We recognize that we have fantastic scientists, and so we invest in those scientists. So we don't try to spend the money here in Lugano, but we spend it, a large part of it, at the various universities, ETH, in Zurich, and we spend it at the university in Lugano. So I mean, not here in CSCS, but we spend it in Lugano at the university, of course. And at the same time, we maintain at CSCS the relationship to we provide the IT infrastructure, but also the relationship to the vendors. And the vendors in this case are Cray, IBM, through the collaboration with Rüschlik on Zurich Lab. And we do have in Switzerland also a company, Supercomputing Systems, and Tony Gunzinger is smiling there. That is actually a very important asset we have in Switzerland. You need some of your own bases in your own country to do this development. And then these create these interdisciplinary teams that do all this complex development. And I think we do it rather successfully. So that's the approach. And this is what we plan to continue. This is basically the slide where we started in 2009 and we installed, one of the first measures was to install Monte Rosa. So part of these 172 million we actually spent already then because you cannot develop computational science if you don't have a substantial machine. So we did have some very skilled people in the ETH board that sorted out, how we can move funding around and made this possible. We did have the help from the Swiss University Conference, and some of the leaders are also sitting in the audience that have really helped putting this HP2C platform together that allows us to prepare these science teams. And then we started construction of the building 2 years ago, and today we have this new building, okay, which is one of the major milestones because this is now what allows us to take together, but to go forward. The building, the investment we have in science communities. And so now we are going, in the next 2 or 3 years, we will see the development of a new petascale computer here at CSCS. I cannot tell you the details of how this computer is going to look like for the simple reason that I don't know at this point. Because we are not just buying a computer that is out there. We are building something together with companies based on the experience that we have on these applications. The university conference is in the process of looking at a project that we proposed as a successor to this platform for the next fiscal period in Switzerland. So we will learn some lessons we learned here, and then we will make it even better in the future in order to prepare the design of then yet the next generation of systems that will come. And these are, I call, pre-exaflop systems, and I'm confident we will help mold the exascale systems that will be here at the end of the decade. So this is roughly the plan, how things are going forward, and I'm going to learn much more myself about the details of the plan as we move forward, because it is, in fact, work in progress. It has been since 2009, and you can be confident that we will move forward about at the same speed, because we do have the support in Switzerland to go forward from ETH, from the ETH board, and also from the commune of Lugano, Ticino, and the scientific community in Switzerland. So I'm very excited about this.